Our last few lectures have talked about how we use FFTs in frequency response to solve vibration problems. So given the force and knowing something about the properties of the system, how do we calculate the response? Today we're going to flip that around and talk about how we can take a structure such as this bridge here, and we can take measurements, apply forces, measure responses to figure out what the system is that made that response. So usually our goal is to figure out what the modes of vibration are, what the natural frequencies and damping and mode shapes are. So let's dive right in. Remember, the very basic idea behind a frequency response is that it's a scalar that relates the amplitude of the input. So if we apply a harmonic input and f is that amplitude, it's a function that relates that amplitude to the amplitude of the response. So if the simplest way that we could measure an FRF would be to apply a sinusoidal force, a sine or cosine here, right, with a known amplitude and phase, and then we could measure the response, and we could take that sinusoid and figure out its magnitude and phase, right? And then in the complex domain, we could just take the ratio of those two, put them in polar form, for example, take the ratio, and we'd have the transfer function. This would be a complex number. So that's the simplest approach. And this approach is used still in some industries. This approach is very robust to nonlinearities, also very accurate in terms of damping. So one place that this approach is often used is in aircraft ground vibration tests. They will excite the various modes of the airplane. For example, if they wanted the mode where the wings are bending up like this, they could apply two forces in phase here. And this is actually frequently done in the aircraft industry. They'll drive each mode to resonance and use this approach to calculate the transfer function and to calculate the damping at resonance. And it's robust to nonlinearities, so things like slip and in joints, in flaps, wing flaps, things like that, don't tend to perturb this method. But the downside to this approach is it's very slow. How long does it take to get to steady state, right? Well, for an airplane, say the first natural frequency might be about 1 hertz and the damping might be about 1%. So the time constant's 16 seconds, 8 time constants, we're talking about 2 minutes. And all of that gives us only one frequency. So if we're trying to measure the transfer function, at many frequencies around a resonance, right, we need to multiply those 2 minutes by all of the different points you want to measure. And so this approach just tends to be expensive in terms of time, resources. So what can we do to improve on this, or at least improve on it for some cases? We can use the FFT. So suppose instead of applying a sinusoidal force, we apply some other force. Here I've drawn an impulse. And suppose we measure that force, and we measure the response that we get due to that force. And then we can use the FFT to convert, say there were n time samples of each of these. We can convert that to n over 2 plus 1 frequency samples. So we would know the force as a function of frequency and the response as a function of frequency at all of these different frequencies. And then we could use the same approach to estimate the FRF. We could just divide those complex amplitudes from the FFT, and we would get an estimate for the transfer function. The one potential downside to this approach is if we apply a force such as what I just showed in the frequency domain, so this is versus time, in the frequency domain, that force will look something like this. And the length of the pulse governs where these little zeros happen. But these can become a problem because at all of these points we're going to divide by 0 in this denominator, and noise is really going to be amplified. And even if those aren't exactly 0, they're small and they can amplify. We're not putting much force in, so the response we get out does not give us a good measure of what really happens. So we could improve on this if we could apply several forces and average the results together, because maybe the second force, would look like that, and as we average those together, we might get a smoother spectrum. So that's the approach that I'll talk about next, and that's really what's used in practice in industry all the time. So the idea is that rather than just applying one force, we apply, say, 3 of them here, right? So we just repeat the experiment 3 times, and I'll call this F1 and X1. So we would say here that we have 3 averages. If we take all of those measurements, each of those measurements should obey these same equations, right? And if the system doesn't change, the transfer function should be the same in each case. So we can actually factor it out, and we can write this as a system where we have 3 equations and 1 unknown. So this is what's called a least squares problem. Or it's an overdetermined system, but the solution that we can get to this is at best a least squares solution. So it's a solution that will fit in the least squares or average sense. We'll talk about that a little more in a second. Okay, so the way that works, if you remember your linear algebra, is that we would take this equation and we pre-multiply both sides by something. In this case, we use the complex conjugate transpose of this force vector here. And remember, this is all at one frequency. We're going to do this frequency line by frequency line. And if we do that, we get this equation, and notice this is 3 by 1 times a 1 by 3. Got that backwards. This is 1 by 3 times 3 by 1. So this ends up being a scalar equation, and now it can be inverted. And so what we do when we multiply those together, we basically just get the summation of each force with each response. So notice it's always 1, 1, 2, 2, 3, 3, right? In general, we can write that equation this way, and this is something that's seen often enough in signal processing that they give it a special name. We've defined, so this is the definition of the cross spectrum. So the definition of that is the average of the FFT of X times the FFT of F. Complex conjugate. And similarly, if we put in, if we wanted SFF, we just replace the X with F, and that would just be F times F star, or magnitude of F squared. So our equation here just becomes this scalar equation, and we can solve that this way, and I've written it in a special way because in a minute we'll see that this equation will also hold for a multi-input, multi-output case. So this is called the H1 solution, and it's kind of a tricky name because it doesn't mean response point 1 or point number 1 on the structure. It's also not the same one that we have here in terms of average number 1 or time history number 1. But it's called the H1 solution in the literature, and the alternative solution is called the H2 solution, which we'll talk about in a second. So H2 is just an alternative way of solving the same thing. Rather than pre-multiply both sides by F, we could pre-multiply both sides by X, or X complex conjugate transpose. If we do that, we get a slightly different equation here. And now, whereas here we're inverting the force autospectrum matrix, or the cross spectrum between the force and itself. So a spectrum between a force and itself we call the autospectrum. We're inverting a cross spectrum. And there are statistical reasons why one or the other can be better. In cases where the force has low noise, this is considered to be the least biased, the most accurate. In cases where the response sensor is thought to be less noisy, this approach can be better. And you can show that it's unbiased as long as the response sensor noise is small. So anyway, that's an aside. In practice, the H1 solution is really the one that's used the most. People tend to believe that the force signal has lower noise, so that's one of the reasons. There are also some issues that come up with H2 when you have a multi-input, multi-output system. So we'll mostly just use the H1 solution in this class. So we can extend all of this to a multi-input, multi-output test. So let's say, I've already stacked everything together here, but let's say in each test we measure at N0 output channels, and we apply forces at Ni input channels. And so we could take, again, all of this is just at one frequency. We could stack up the values, the FFT values. Here we'd have, this is a vector, where we'd have the force at drive point 1, the force at drive point 2, and so on. And we stacked all of those together at the same frequency. And then we'll also recognize that if we do a second test, a second average, and we put it in the second column here, when we do this multiplication, we'll get h times f on this side equal to x2. So we can just stack all of the measurements in this way into two matrices. And if we post-multiply by the Hermitian, or the complex conjugate transpose of f, we get a system that we can solve again. And so this uses the matrix definition of cross spectrum. Which I forgot a transpose here, or somehow that didn't copy. But so the definition of cross spectrum for a vector matrix combination is this. It's the first vector times the Hermitian, or complex conjugate transpose, of the second. And so we multiply these together. And the interesting thing that happens here is that you get just a product of the vector, right? This is a tall, skinny vector. This is a row vector. So we get the product of these rank 1 matrices, or these vectors that give us rank 1 matrices. But if we average over enough measurements, we would hope that we can eventually build up a full rank matrix that we can invert. Okay, so anyway, that same formula again works, and we could have a whole discussion on when this matrix is invertible and when it is not, but we'll just leave that for you to study on your own. Okay, and again, these are the advantage to the simple approach is it's a least squares solution. So given given a certain frequency, a bunch of response measurements, and a bunch of forces, h is just a scalar that relates those two. So it's like we're fitting a line to a bunch of data. So if we were to define the distance, the error, or the distance between each of these lines, or each of these points, and h, the H1 solution minimizes the sum of the squared errors. So that's why we call it a least squares solution. And I can just show you a case where this simple method wouldn't work well. The alternative, the simple method would be to just calculate h from each pair. That's kind of like estimating the slope here, estimating the slope there, and then averaging all of those slopes together. And I've deliberately drawn this so you can see a problem. If we try to use this point to calculate h, well, the force happened to be 0 right at that frequency. And so when we divide, we'll divide by 0, we'll get an infinity, and that will destroy the average here. And so that leads to the poor statistical properties of this simple method. So again, that's why these methods are used. The other thing that's nice about these methods is notice that even if we have a large system with lots of data, this can be built as a running average. So we can take the jth measurement, we take the first measurement, we compute this, we take the second measurement, add it, add the appropriate scale factor, right? Take the third, the fourth, and we can throw away all the past time histories and just keep the running average. And in the early days when memory was short and hard drives were small, this was necessary to make measurement even possible. Today, more and more, it's possible to record time histories, and most important tests, the time histories will actually be streamed and recorded. And you can get gigs and gigs of data, but the test is so expensive it's worth saving all that data. A lot of the analyzers, though, still use this approach and will only store the autospectrum and cross-spectrum. They won't store all the individual time histories. In many of them, in fact, to get time histories, you can only get the time history for the last block. So if you did 3 averages, you could get this time history, or you can store and get the FRF or these autospectra. But you have to go through some extra steps, what's called throughput recording or something, if you want to actually record the time histories. Okay, so that covers FRF estimation. The only thing we haven't talked about is what we would do if our force was continuous and random. So suppose our force is like this, it goes on and on, there's no periodicity to it. The response that we get would also kind of have a similar form, right? So we can use this same approach here, and we can break the data into blocks. So here I'm showing, block 1, x1, and if you're using random data like this, it's customary to actually overlap the blocks, because there's no reason that you have to treat each block as completely separately. You could even shift them one sample, and the signals, the FFTs of the signals will be different. Okay, but this does cause a little bit of a problem, because we'll have leakage if we try to take the FFT of these signals without doing anything to it. So what's done is to multiply the signals by a window. For example, a Hanning window has this shape that I sketched in right here. And when we multiply the force times that window, we get a force with an envelope on it like that. And the force now starts and ends with 0 initial conditions. And the same would happen for the response. And we get something that it behaves much better in the FFT. So this is the approach that's typically used. That also explains why we use the overlap, because we've taken all of this data here and we've weighted it lower than the data in the center. So if we take a second set of data, a second window, now this will kind of emphasize some of the data that was lost in the first average. So that's one reason why a 50% overlap is often considered to be the optimum. Okay, so there is a consequence to windowing, though. and we won't get into it in a lot of detail here, but this window function, which is simple in the time domain, in the frequency domain it has kind of a picket fence spectrum like this. And multiplication in the time domain corresponds to convolution in the frequency domain, which basically means that whatever the true frequency is here that we're trying to estimate, in our signal we're going to get little ghosts of that on a picket fence at lots of frequencies above and below that. And then we'll get the same thing for the next frequency and the next one. And so all of that can add up to causing some distortion in the signals. So so that's something that we have to watch out for. What's nice that happens again is that if we have a long enough time window relative to the time constant in the system, that distortion will usually be small. And why is it that the time constant matters? Well, remember that the FRF that we're trying to measure has a peak, right? And the width of that peak is related to 2 zeta omega n, which is related to the time constant. So if we keep t small, and so we keep these points in this picket fence close together by making t large, and which causes the frequency spacing omega 1 to go down, we can get a lot of points in the peak of the FRF, and then this picket fence has a lot of time to decay down before we get to our next frequency line of interest. So that tends to minimize distortion. Let's look at a MATLAB example of this really quickly. Okay, so we saw this example before. Let's just show you again. If we have the case where the natural frequency is 17, or the frequency we're trying to measure is 17 and it's halfway between frequency lines, here's our signal with error due to the windowing. Right, so now if we apply a window to the signal before we take the FFT, and let's see, let's put this in figure 11 so we can tell things apart. 11 and 12. Now if we run this again, notice our time signal now has the window applied. And what does that do to the FFT? Here's the FFT that we get with, here's the FFT we get with the Hanning window and without. And notice that here we get 2 points much closer to the true amplitude. So there still is leakage. We've split this frequency into 2. But the estimates are closer to the actual amplitude estimate. Also the roll-off is faster, right? We're more quickly going to 0 as we get away from that frequency. So we haven't bled the energy into as many frequency lines. All right, so the window tends to help improve things and improve the quality of the FFT. And if we improve the quality of the spectrum, we'll improve our estimate of the frequency response function. So how can we use all of this information to measure accurate FRFs? Well, we can think of a couple things. One thing that we can think about is in the time domain. As we've said before, if we apply an impulse, we need to allow enough time for the response to go to 0 before we end our window. We need a large enough period so that we don't get leakage. And it turns out that that same thing is true even if these were random responses. If F is random, and the response is also random. That same principle holds, because if you think about it, the response we have here may depend more on what was happening before time 0 than it does on the force that we're actually applying right now, right? T is a measure of how long it takes for a transient to decay. So if we want this response here to be a strong function of the force that we've applied here, we need to allow enough time for the signals to decay, for the transients to decay, so that we can focus on the here and now. So, so that's one thing to think about. And then we also need to make sure that all of the frequencies are excited. So we've already kind of mentioned this, but if we have f of omega and x of omega, you know, if our force signal looks like this, then we're not probably going to get a very accurate estimate of the response. So, you know, if we had a force signal that looked like that, our response signal, you know, might look like this. And all of these other modes here that we're trying to measure have very low amplitudes and might fall down in the noise floor. So we need to apply enough force. We also talked about the problem of impulsive forces, right? And if we don't use any averaging, we have all these places where we have problems. So really, that's all there is to it. Minimizing leakage and making sure that we get enough response. In terms of getting enough response, it is tricky. I mean, it depends on how much noise we have in our system. And so sometimes we can get away with pretty weak signals if we have a good signal-to-noise ratio. You'll probably see that when you do the next lab. Once we get an FRF, how do we tell if it's accurate? This just kind of takes experience. You kind of learn to look at them and learn to see what to expect. One thing we can do, and that you will do in the next lab, is to take the measurement, the black is the measured FRF, and to fit it to the analytical function for a linear system. So we fit 4 modes to the data, and then we overlay the data and the fit, and here we even show the difference between those to kind of accentuate the differences. And if the data fits well, then we know that we have an accurate, or what could be an accurate linear FRF. That doesn't tell us that our calibration isn't wrong or anything else went wrong. But it does give us an idea what the noise floor is in our measurement. Any leakage errors will show up here. So it's typical to have some amount of leakage even in really good FRFs. To take data long enough to make leakage go away completely is usually not too practical. So this is what I would see and typically think of as a really good set of data, or a pretty good set of data. Except maybe down here if you were interested in the low frequencies. This next slide shows an example of a not so good set of data. So here we see a lot of leakage right around this peak, so we're not able to fit it very well with the analytical model. And you can actually even see the picket fence here due to the windowing and the leakage. Here a Hanning window I don't think was used, but this picket fence effect still we saw, probably due to either a rectangular window or something in the force spectrum. But in any event, this is not a very good set of data. You can see the curve fit doesn't fit too well. By the way, ignore this peak. There's actually 2 modes at that frequency it appears, and so this one is just a mode that wasn't fit. But at all the other peaks we see quite a bit of leakage, so we know we should go back and take this data again. Often you can get a good idea if you look at the phase. So by the way, this is the average of lots of measurement points. If we just look at a single FRF, we can get an even better view sometimes. Noisy measurement will especially suffer in these anti-resonance areas, right? So those can be telltale signs. Also, looking at the phase is often telling. The response is always quite peaky, but the phase should have these nice phase shifts of 180 degrees every time we go through a resonance. Here's one that actually looks pretty good, right? And maybe there. But many of these, the phase is really jumping around, so you can tell that things are noisy. So those are some things you can look at. Otherwise, it just takes some experience and trial and error, and that's the fun of an experiment, is adjusting things and thinking about what the measurements mean and figuring out how to make them as good as possible. All right, so that concludes our lecture on estimating FRFs.